Okay, I am going to talk to you about the beginning of the universe, which is sort of a strange place to find oneself as a scientist because it inherently becomes an interdisciplinary problem. The thing is that very early in the Big Bang, as we'll see, the universe was very hot and very dense. And at very, very early times in the universe, like fractions of a second after the Big Bang, the relevant physics, the energies of the temperatures are so high and the energies of the particles are so high that the relevant physics is particle physics. So the early universe is where the physics of the very large, the cosmos, galaxies and clusters of galaxies and so on, meets the physics of the very small out of elementary particles and fields, closing in a full circle at the first moment of time. And it's a subject that combines astrophysics, general relativity, particle physics in interesting and novel ways. And we'll see how that very much reflected in the topics that we talk about tonight. So let's talk about the beginning of the universe, the beginning of the world. The universe had a beginning, and we know when it was. It was a little less than 14 billion years ago. The more precise number is about 13.8 billion, and the uncertainty on that number is about plus or minus 200 million years now. So we know the age of the universe to within a few percent, which is just a remarkable achievement when you think about it. And the fact that the universe had a beginning at all is a bit of a mysterious thing, right? It leads to other questions. What was before it? What did it come from? What was the cause of this, right? So in many ways, this realization that the universe was not a static and infinite place, this Cartesian universe of Isaac Newton and René Descartes, and that was of all of classical physics, where the universe was a static, eternal arena in which physics took place, but that instead the universe is a dynamical thing and actually had a beginning 14 billion years ago, is arguably one of the most consequential discoveries of 20th century science. It completely changed our pictures of where we are and what our position, what our place in the universe is. And so let's look at cosmology in ancient times to start with, right? So this is a diagram of the Ptolemaic geocentric universe with the Earth at the center, the Moon, Mercury, and so on, all of the celestial bodies, the planets orbiting on circular orbits with epicycles around the Earth at the center, outside of which is the firmament of the stars, and then beyond which are the Empyrean realms and where God lives, right, on the outside. And this was first of all a very hierarchical place, right? So the Earth is at the center, which means in some sense that we're special. Right. And the way Thomas Aquinas put it was that the cosmos is God-ordained and man-centered. And the Earth in Aquinas's picture, in this classical picture of theology, was a special place in the universe. There was something particular about us. We're at the center. In fact, we weren't like special in the sense of being the best place in the universe. We're kind of special in the sense of being the worst. We're like the cesspool of the cosmos, where everything sort of sullied and imperfect lands, right? But this also was reflected in Aristotle's system of physics, in the sense that motion in Aristotle's idea was, in a sense, unnatural, right? So that any moving object would gradually come to rest relative to the surface of the Earth. Any material body, motion had to have some sort of a cause, and the natural state of all material bodies was at rest. Furthermore, there was no concept of universal physical law. The laws governing the motion of heavenly bodies and the laws governing material bodies on Earth were not the same thing at all. The ethereal bodies were constantly in motion. Terrestrial material objects' motion was an unnatural state. And so there was no essential, the modern concept of physical law applying everywhere in the universe was completely absent here. So, and in particular then, Aristotle made an argument of the necessity of a first mover, cause and effect. The idea, since motion in Aristotle's picture, wow, why is it smunched up like that? I don't know. In Aristotle's viewpoint, that since motion is unnatural, Aristotle wrote that since everything is motion must be moved by something, there must be a cause to any motion. Let us suppose there's a thing in motion that was moved by something else in motion and that by something else and so on. The series cannot go on to infinity, so there must be a first mover. And Aquinas, of course, identified this as a deity. It was considered in Christian theology to be a proof of God. Copernicus changed everything. Copernicus's heliocentric system, he was, of course, not the first person to propose a heliocentric cosmology, but he was the first person to sort of situate it in a revised notion of physical law. Copernicus wrenched the Earth from its place and set it in motion in the cosmos. And in so doing, he set the stage for Newton's great unification of the Earth and heavens and the laws of motion and gravitation. Newton's realization that the force pulling an apple to the ground is the same force that is holding the moon in orbit around the Earth and the planets in orbit around the sun completes the destruction of Aristotle's hierarchy between the laws governing terrestrial bodies and those governing celestial bodies. It introduced a concept of universality. And in so doing, we have realized that we have always lived in the heavens. We are creatures of the cosmos. We are, in a real sense, just ordinary parts of the larger cosmos. And of course, Copernicus realized that in order to have a moving Earth, any kind of a sense of a moving Earth, it required a notion of relative motion, because in order for us to be moving along with the Earth without sensing its motion, then Aristotle's idea of absolute motion, of motion being something unnatural requiring a cause, had to be modified. And Copernicus really was the first modern scientist to write down a notion of relativity, of relative motion. In that, in his work De Revolutionibus, he wrote that every apparent change in respect of position is due to motion of the object observed or of the observer or an unequal change of both. So he took Aristotle's concept of absolute motion and replaced it with an idea of relative motion. And this was necessary in order to make sense of a heliocentric cosmology in which the Earth was moving instead of stationary. And this completely changed our picture of how the universe worked. And in particular, it was Isaac Newton who really took this idea of universality of physical law and applied it. So saying that if we could understand the thing that makes an apple fall to the ground, we can understand what makes the galaxy rotate, or the planets rotate around the sun, and that Newton's law of gravity applies not just on Earth, but everywhere. And this was a tremendous, an amazing intellectual feat to realize this truth. So in modern cosmology, we take this Copernican principle, the idea that we are ordinary, and extend it into what's called a cosmological principle, although I think it really is just simply an honest application of the Copernican idea that the Earth is not in a special position in the cosmos. The cosmological principle is an extension of that, saying there is no place has a special position in the universe. Every place, at least in some average sense, is ordinary, right? So that there's no preferred space. And that immediately tells you, and this was realized by Copernicus and by his contemporary Giordano Bruno and other people who were thinking about this, which means it means that the universe can have no center and no edge, right? Because these would be special positions in some sense, right? So there can be no boundary to the universe and there can be no center to the universe. And this is central to our picture of the Big Bang. And I think that there's a lot of misconceptions about the Big Bang being, I think a lot of people think of it as some sort of cosmic seed that explodes, like some sort of little dense round thing that explodes and sends stuff going out in all directions. That's completely wrong, and you need to forget about it, right? Because in fact, that center of the explosion would be a special place. It violates the cosmological principle. That's a non-Copernican idea. So a better way to think of the Big Bang is an analogy like this. So imagine I have sort of a stretchable sheet of rubber or latex or something like that, and I draw an even grid of squares on it. So each of these squares is exactly the same size as every other one, and so there's no particularly special point on this. In order for this to fully satisfy the cosmological principle, it has to be without a boundary. So further stretch your imagination a little more and imagine this grid going off infinitely in every direction. So I have an infinitely large grid of absolutely identical squares. This satisfies the cosmological principle. Every spot in this grid is exactly the same as every other spot. There's no center, there's no edge, there's no special position. So now, when the universe expands, right? Imagine these squares getting bigger with time. And as these squares get larger, it still is completely homogeneous. Every spot in this grid is exactly the same as every other spot, but everything has gotten further away from its neighbors. Everything is moving away from everything else, but in such a way that it retains this idea of homogeneity. Right, and in the real universe, you can imagine space being filled with identical cubes rather than a two-dimensional analogy here. It's just harder to draw, right? So in 3 dimensions, you might have a grid of cubes where all of these cubes are getting bigger and bigger with time. So this infinite grid of squares, the squares are getting bigger and bigger. Everything is moving apart from everything else. And so if we're sitting, for example, at the intersection of these squares here, and we're looking out at these other galaxies, let me back this up a little bit, right? So if we're sitting here and we're looking out at galaxies that everybody sees themselves at rest with respect to this grid. So as the grid expands, it carries these galaxies with it. And what we see is all the galaxies, when we look out, we see everything moving away from us. And furthermore, it's not hard to convince yourself that in this kind of expansion, that the further away something is, the faster it's moving away from you, because the amount of the distance it moves depends on the amount of space in between you and it. So this a space like this actually reproduces the linear Hubble law of saying that the recession velocity of a galaxy is proportional to its distance, or its redshift is proportional to its distance. So this is a better picture of the expansion of the universe. There's no center to this. Every point is identical. Galaxies just sit at rest with respect to this, what's called a co-moving coordinate system, and they all move away from each other as that expands. And everyone sees themselves at rest in the center of this expansion with all the rest of the universe moving away from them. If you were in another galaxy, you'd see the same thing. You'd see yourself at rest, and you would see the Milky Way moving away from you. So what happens when we turn time backwards? Right, so now we can say, let's take a look at this cosmic expansion and run time in reverse and say, what does it tell us about the very early universe? And quantitatively, you can do this with Einstein's equations for gravity, his theory of general relativity. And so as we go backward in time, these squares get smaller and smaller, and everything was closer and closer and closer together. And as we go further back in time, they get smaller and smaller and smaller and so on. And Einstein's equations tell you that at finite time in the past, oh man, we're having some issues here. These squares would have gone to 0 size. So you plug this into Einstein's equations of gravity, and as you go back in time, all those squares go to a point where they vanish in size at a finite time in the past. This is called an initial singularity. This is the moment of the Big Bang in the standard model of Big Bang cosmology. Notice that even an infinitesimal amount of time after that initial singularity, the universe is spatially infinite in extent. This grid goes on forever. So the Big Bang doesn't happen at one place. It's not an explosion that happens at a spot in space and everything flies away from that. The Big Bang happens everywhere in an infinitely large space at once. An infinitely large, incredibly dense, very high temperature universe springs into being all at the same time, completely homogeneous, and it obeys the cosmological principle. Right, so the universe all the way back to the Big Bang is spatially infinite in this model. Right, and the Big Bang happens everywhere in this infinite space at once. It's a boundary in time, not a boundary in space. And the initial singularity cuts off the past history of the universe at a finite time, and that's when the universe goes to an infinite density at the moment of the Big Bang. So this is a very different picture, I think, than most people have of this. Right, so how do we work out the history of this cosmos, right? In particular, how do we know that this particular weird model of the universe, with it starting out in this very hot, dense state in which it then cools, right? So as the universe expands, everything in it gets further and further apart, everything gets less dense, and when you let something expand, it cools, simple thermodynamics, right? So the universe would have started out very hot, and as it expanded, it got colder and colder. And in order to do this, in order to work out the history of the universe, we need to use Einstein's theory of gravity, which in the words of John Wheeler can be summarized as matter tells space-time how to curve, and space-time tells matter how to move. And so it's a snake eating its tail. It's a nonlinear process where the curvature of space is created by the matter that lives within it, and the motion of the matter is governed by the curvature of the space that it has created. So in order to understand the history of the universe, we have to describe the stuff that's in it. And cosmologists divide stuff into 3 kinds. The first is just called matter. And what a cosmologist means by matter is anything that is sort of just like atoms or dust or gas or maybe dark matter particles or something like that, anything that can be described by more technically a non-relativistic particle, right? Something that's basically at rest. And so imagine if I have a cube now, so I'm doing this in 3 dimensions. So imagine I have a cube full of like hydrogen atoms or something. If as the universe expands, that co-moving cube gets bigger, but the number of atoms inside of it doesn't change. So the atoms, the density of the atoms drops as the inverse of the volume of the box, right? They become less and less dense. These atoms become more dilute because the space is expanding, but the number of atoms is fixed, right? So the amount of energy per unit volume in this box drops with expansion. The second kind of stuff that cosmologists use, we just call radiation. And this might be photons or leftover from the Big Bang. We'll talk about those, or neutrinos, or any essentially relativistic particle, anything that's massless traveling at around the speed of light. And this this radiation also dilutes with expansion, but it dilutes a little more quickly than the matter, because in addition to the number of particles, the number density of particles, the number per unit volume dropping with the expansion in exactly the same way the matter does, the radiation also has redshifts. It loses energy because the wavelength of the photons stretch as the expansion continues, right? So when a photon propagates through this expanding background, it actually gets stretched out by the cosmic expansion and gets longer and longer wavelength as time goes along. And so they lose a little bit more energy because of that redshifting. And so the total energy in the box dilutes more quickly for radiation than it does for matter. All right, so this stuff, the relativistic things, dilute more quickly than the non-relativistic things like atoms or something. So photons dilute more quickly than atoms, right? The third kind of stuff is called vacuum, which is essentially the energy of empty space. And this will become very important later when we talk about inflation. And basically, if you assume that space itself has some sort of non-zero energy associated with it, and we believe this to be the case in the current universe, this is the stuff that's called dark energy, then if the space itself has an energy to it, then the energy density stays constant, right? So as this box gets bigger, the total amount of energy that's contained in the box actually increases. So if you have a constant, amount of energy per cubic meter and the number of cubic meters in the box grows, if there's more vacuum in the box and the vacuum has energy, then the amount of energy in the box is going to go up. This might seem like it violates conservation of energy, and which is true, it does. Sorry. I mean, energy is not conserved in general relativity globally. There's still a local sense in which it's conserved, but general relativity allows you to break energy conservation in this way. In particular, because it's time dependent. You no longer, and energy conservation is associated with symmetry under time translations. If you have a time invariant system, you have no reason to expect that energy is conserved. And in fact, in cosmology, it is not. It's also the same here with these photons. These photons, a light wave traveling through empty space loses energy due to cosmological expansion. That energy doesn't go anywhere, it just loses it, right? So this is another example of violation of conservation of energy in cosmology. But it's most prominent in this vacuum energy, where you actually just get more and more energy out of nothing as this box expands, if empty space itself has energy. And this is a key to this theory of inflation that I'll talk about later on. So this means that, let me see, hang on. Let me see if I can get this to display a little bit better. I'm not sure why it is crunching up some of my slides. Let's try doing this. From current slide. There we go. Yeah. All right. So this means that because, and now the vacuum doesn't dilute at all, right? So matter dilutes slowly, radiation dilutes more quickly, vacuum doesn't dilute at all. So if we turn time backwards, that means that there are 3 main epochs in the history of the universe. Before about when the universe was about 60,000 years old and earlier, and a temperature of about 10 to the 4 Kelvin or higher, the universe would have been mostly radiation, relativistic species like photons and neutrinos and light particles, right? These diluted away more quickly, and then at about 60,000 years after the Big Bang, the universe transitioned into being matter dominated. So things like hydrogen and helium and dark matter and so on would have been the dominant energy density in the universe. Up until the universe got to a temperature of about 5 Kelvin, a little less, about 3.5, which happened about a few billion years ago. Actually, while there was still primitive, while there was primitive life on Earth, the universe went through another transition in which the matter diluted away, and this residual vacuum energy started to be the dominant component of the energy of the universe, and it is still today. So the vacuum energy now, in fact, makes up about 75% of the energy density of the universe, and the matter and radiation are the other 25%. And because the universe was, everything was squished together, the early universe would have been very hot. And so as we go backward in time and up to higher and higher temperatures, our understanding of this gets more and more speculative, right? So at a very high temperature, we would need a theory of quantum gravity to undo it. We don't have such a theory. That would be about 10 to the 32 Kelvin temperature. Going downwards, so dark matter forms somewhere in here. We don't know really where. The Higgs field gave mass to the standard model particles at a temperature of about 10 to the 16 Kelvin. Quarks form bound state at a temperature of about 10 to the 12 Kelvin. The first nuclei formed when the universe was about 1 second old at a temperature of about 10 to the 10 Kelvin or so. Electrons and their antimatter counterpart annihilated a little bit after that, so on and so forth, all the way down to today. The first stars formed, maybe when the universe was a couple 100 million years old at a temperature of about 20 Kelvin. The current temperature of the universe is about 3 Kelvin, right? So we can work out this thermal history of the universe, and we understand it pretty well, and we have observational constraints back to about 1 second when the first nuclei formed. We can figure out, we can constrain this by looking at the abundance of primordial abundance of elements in the universe today. Anything before that is much more speculative and theoretical. But so here's what we see today, is that the universe, the density of the universe is about 73% vacuum, or this stuff called dark energy. We don't know exactly what it is, but it is well described by an energy associated with empty space. About 23% is dark matter. We also don't know what this is, but we know it behaves differently than dark energy. This dilutes with expansion like matter and not like vacuum or radiation. We know that much. And then about 4% of the universe is all the stuff we know about, everything on the periodic table, the atoms, mostly hydrogen and helium, with trace elements of the rest of the stuff, right? So in fact, we've only actually managed to identify about 4% of the contents of the universe. Everything else we only know about indirectly from their gravitational influence on the things that we can see. So I guess this is job security. There's a lot of work left to be done, right? So that we've only identified 4% of the universe. The other 96%, we really don't know what it is. We just know it's out there because of the way it affects the things we can see. So how do we constrain this with observation? Right? We're doing science here. This is not philosophy. We want to actually use data to constrain these models and to constrain these properties of the universe. And the way we do that is we use time machines. In particular, time machines like this thing, which is the James Webb Space Telescope. Right? Telescopes are time machines because the speed of light is finite. When we look out in space, we're also looking back in time. In fact, the speed of light is not all that fast. Light goes about a foot per nanosecond. So in the time it takes your cell phone to do one computation, light travels about 30 centimeters or about a foot. And that means that on cosmic scales, this is glacially slow. It takes light 8 minutes to get from the sun to us, so that when we look at the sun, we're seeing it as it was 8 minutes ago, not as it is now. When we look at the center of the galaxy, we're seeing it as it was 30,000 years ago because it's 30,000 light years away. It takes light that long to get to us. When we look at the Andromeda galaxy, we're seeing it as it was 2.5 million years ago. If we look at a galaxy a billion light years away, we're seeing it as it was a billion years ago. So cosmologists are lucky, unlike archaeologists who have to reconstruct the past from bones and relics and leftover clues. Cosmologists can actually just look out and see the entire history of the universe stretched out in front of us in the light that is coming to us from more and more distant objects. So this is one of the deepest images of the universe that's ever been taken. This is a recent picture by the James Webb Space Telescope. And what you're seeing here is mostly galaxies. These are some foreground stars here, but all these smudges here are galaxies in the distant universe. And you really should think of this as not just a picture of the universe today, but it's actually a timeline showing you the entire history of the universe back to when it was only a few 100 million years old. The most distant objects in this photograph are almost all the way back to the Big Bang. So the light was emitted from them when the universe was only a couple of 100 million years old. And you see in objects just stacked up at different redshifts, right, at different amounts of light, different amounts of travel time, you see the whole history of the universe spread out, the history of formation of galaxies, all of these things, you can just see them in a single photograph. So the most distant object that has been found by the James Webb Space Telescope so far, and this is a very recent result, is this guy right here, which is at a redshift of 13.2. That means that the light from it has been stretched in wavelength by a factor of 13.2. So all the photons that would have been emitted in optical wavelengths are now in the infrared. That's why the James Webb Telescope observes in the infrared, because otherwise you wouldn't see these distant objects because the light is stretched so much by cosmic expansion. And this corresponds to a look back time of about 13.6 billion years. So that little red smudge, you're actually seeing it as it was 13.6 billion years ago. The universe is only 13.8 billion years old. So this was a galaxy that you're seeing when the universe was only about 200 million years old. And in fact, this is so far back, it's causing problems for our standard dark matter-based models of structure formation, is that there shouldn't be big galaxies that early in the universe. And so this is sort of a bit of a puzzle, because we didn't expect to see large, well-formed halos that far back at about 200 million years. So this is already starting to challenge our theories of structure formation and so on. Note that this does not mean the Big Bang didn't happen, as you might have seen in the press, right? This just means that our standard dark matter-based theory of structure formation needs some modification, but the Big Bang theory is holding up really well. This is exactly what you would expect in a Big Bang cosmology, is you're seeing these very old, very highly redshifted galaxies in these images from Webb. So we can just actually just look back out in space and look back in time, and we can see the whole history of the universe as it happened. We don't have to guess. It's not speculation. It's not just mathematical model fitting. You're actually observing that entire history. So here's a remarkable picture. This is a map of galaxies, right? This is by the Sloan Digital Sky Survey. So in this picture, this is 200,000 galaxies and quasars. So each dot in this picture is a galaxy like the Milky Way, with 100 billion or 200 billion stars in it. And this is the real distribution of actual galaxies in our universe. This is a real three-dimensional map. If you look, and it's wedge shaped, because if you look at a strip on the sky, so we're here, and if we observe a strip on the sky and then expand that depth out into distance away from us, then it looks like a wedge, right? So we're sitting here and we're looking out in the universe. And this is a look back time here of about, so this is a redshift of 5, which corresponds to a look back time of about 12 billion years as the most distant objects in this map. So we are now producing the first three-dimensional maps of the universe out to distances of look back times of about 12 billion years, a little bit more. And we're actually seeing how the galaxies and the structure in the universe evolves. We can directly observe all of this stuff and use it to fit our models and understand the processes that are going on in the universe. So you don't have to guess. It's not theory. You can just go out and observe it. So as we look out in space, we look back in time, right? But the universe has a finite age, right? So we have a look back time of 12 billion years. You know, this thing is at a look back time of about 13.6 billion years, but the universe is only 13.8 billion years old. So if we look out, if we could build a telescope that looks far enough out in space, far enough back in time, we would see the Big Bang happen. And in fact, no matter what direction we look, if we look far enough back in time, because the Big Bang happened everywhere in an infinite space at once, we would see the Big Bang as it happened in that direction, right? This is the idea of a cosmic horizon. So imagine at the moment of the Big Bang, you have one observer who lets a flashbulb go off, or a supernova happens or something. He sends out a light pulse, right? That light will travel out from him at the speed of light, but because the universe has a finite age, and the age of the universe, it can travel a finite distance. It's not hard to imagine that that's also as far out as he can see. If this is, so the radius of this sphere of light he sends out is the speed of light times the age of the universe. So he can't see anything out of that circle. So despite the fact that the universe is infinite, we can only see a finite patch of it because the universe has a finite age and light has a finite speed. Anything outside this circle, like this observer, the light from him hasn't had time to get to him yet because the universe isn't old enough. So now as the universe expands, our observable universe, the little patch of it that we can see, expands outward from us at the speed of light. It gets bigger and bigger, so we see more and more and more of this universe as time goes along, and then eventually this guy can see this guy because the light from this guy has had time to reach him, and so we actually only ever see a finite part of the universe. So what we actually see when we're sitting in this infinitely large homogeneous space is we see ourselves at the center of a sphere, a spherical universe, and the edge of that sphere is the Big Bang itself. And if we look out from here all the way out, if we could see all the way out to the edge of this, what we would see is the Big Bang, and we would see it happening in every direction. So the Big Bang isn't a point out there in space, it's a sphere with us at the center. Now we can't see all the way out to the Big Bang itself. I mean, one more point on this is an observer-dependent effect. It's like the horizon on Earth, right? If I stand here, I can only see out a certain distance because of the curvature of the Earth. Somebody else standing in a different spot will have his own horizon, and those may or may not overlap. So everybody sees them, and in cosmology, it's a similar thing. Everybody sees themselves at the center of their own observable universe, and those observable universes may or may not overlap. But it's an observer-dependent effect, just like the horizon is on Earth. Everybody sees the same thing. It still obeys the cosmological principle. Now, we can't see all the way back to the Big Bang because very early on, the universe was so hot and dense that it was opaque. You want to think of it as like a big, thick fog that's scattering the light so rapidly that you can't see through it. This is the early universe when the hydrogen and helium in the universe, the atoms, right? So the only elements that were produced in the Big Bang were hydrogen and helium, and everything heavier was produced later on in the cores of stars and supernovae and things like that. And so the very early universe where this hydrogen and helium would have been extremely hot, and it would have been so hot that it was ionized. The electrons were stripped away from the nuclei, and so you would have had this plasma, which means that you have the positively charged nuclei here. The electrons would have been freely roaming around in space, and the light scatters very strongly off those free electrons. And so this would have been a very hot, dense, glowing gas that you couldn't see basically your nose in front of your face because it's this thick fog that the photons are scattering rapidly. When the universe was about 400,000 years old, a little less, about 380,000, and the temperature of the universe dropped below a temperature of 3,000 Kelvin, these ionized atoms would have captured the electrons and gone from ionized to being electrically neutral, so that there was a transition that happened where all those once the gas got cool enough, these electrons would be captured by the nuclei. And then the universe at that instant, very rapidly, became transparent, and all this light that was trapped in this ionized plasma would be released and starts free streaming through space. The universe was transparent, and this light is still out there. Because the universe is expanding, it's gradually cooling. So at this time, it was 3,000 Kelvin. It would have been like a very hot oven. It would have been sort of a glowing red oven if you would have been able to see it with your eye, right? It would have been a very inhospitable place, but it would have been in the visible wavelengths. But the universe since then has expanded by a factor of about 1,100. And so these photons have increased in wavelength by about a factor of 1,100, and now they're in the microwave wavelengths. And this is the cosmic microwave background. So this is light that is directly left over from the Big Bang. And if we look back to a look-back time of just when the universe was only about 400,000 years old, we see this light coming to us from what's called the surface of last scattering. So this is now, these wedges here are the Sloan Digital Sky Survey. This is these maps of galaxies. Now this is showing the look-back time all the way out to 13.8 billion years. And as far out, but you can't see all the way back to the Big Bang. You can just see to this, what's called the surface of last scattering, the point where the universe went from becoming opaque to being opaque to becoming transparent. And the light you see is primarily in the microwave, and this is called the cosmic microwave background. So this is correct to scale. This is as far out as we've gotten our maps of the galaxies. These gaps in this map are because of the plane of the Milky Way that we can't see through our own galaxy well enough to measure the positions of other galaxies. But this is a remarkable picture because we're actually starting to map out significant fractions of our observable universe quantitatively. This is real data. This is the real positions of real galaxies again. And this image here is a real image of the cosmic microwave background. And so here is, so we are at the center of this sphere. This is the sphere of the sky looking out at this light left over from the Big Bang. So we don't see the Big Bang, we see this glowing sphere of light that is the light that was released when the universe became transparent at an age of about 400,000 years. And this is showing the Planck satellite image of the fluctuations in this. So this is the variations in the temperature of this primordial light, vastly exaggerated, right? So all these photons, all the light coming to us from the early universe is exactly the same temperature to 1 part in 100,000. And these little 1 part in 100,000 variations, the red things are hot spots, the blue things are cold spots, are caused by the primordial density fluctuations in the universe. These hot spots are a little denser than their neighbors, and these cold spots are a little less dense. These are the seeds that later collapse to form galaxies and structure in the universe. So you had these when the universe was 400,000 years old, you had these 1 part in 100,000 fluctuations in the density that created these variations in the temperature that you can map out with satellites now. So this is real observations of the light coming to us from the Big Bang. And then all of these little overdense regions would then collapse under gravity, and they were the things that form stars and galaxies and so on, right? So we can actually observe, this is a real picture of the universe when it was 400,000 years old. We're seeing the primordial seeds that formed all of the structure in the universe before any of that structure formation happened. We can observe it directly. So this is very powerful, and this has been a 30-year effort. So in the 1990s, the COBE satellite made the first maps of the cosmic microwave background fluctuations. In the 2000s, the WMAP satellite made far more accurate measurements of it. And then in the 2010s, the European Space Agency's Planck satellite made this definitive map that I've shown you, which really gives extremely high precision measurement of this. And from this, we can measure, for example, the curvature of the universe. We can measure the density of the dark matter. We can measure the density of the baryons, the hydrogen and helium. We can measure the neutrino density. We can measure all of these things to sub-percent precision. So this is super high precision measurements of things like the densities of different materials in the universe. It's an incredible data set. And ironically enough, this picture of the universe with us at the center and the cosmic microwave background, and finally the outer sphere of the Big Bang around it, is remarkably reminiscent of Ptolemy's cosmology, right? Except that this now obeys the cosmological principle in the sense that everyone in this infinite universe sees exactly the same thing. There's still no special position, but we look like we're special because of this effect of looking out in space being looking back in time. So instead of the Empyrean realm or the sphere of the fixed stars at the edge of the cosmos, instead what we have at the edge of our cosmos is the Big Bang, and beyond that there's nothing at all because the universe had not existed before that. So this is what we see. This brings up some puzzles, in particular this incredible homogeneity of the cosmic microwave background. Remember that the observable universe is small early on and gets bigger later. So if the universe is 1 million years old, the observable universe is only about 1 million light years in radius. Actually, expansion effect's about double that. It's about 2 million light years. And so you can't see, and then when the universe is 10,000 years old, the radius of the observable universe is only about 10,000 light years. So if you look at the cosmic microwave background and say, okay, if I look at a point here, this photon is coming to me. When that photon was emitted, the observable universe at the time that photon that I'm observing here was emitted into space, the observable universe was only a few 100,000 light years in diameter. So this photon's observable universe, when it was emitted, is only about that big, and on the sky today, it's only about 1 degree, about twice the size of the full moon. This photon over here, his observable universe would have been that big, and so on. And you can kind of see this, actually. You can kind of see that the characteristic size of these blobs is about all the same. That's because the blobs couldn't get any bigger than the size of the observable universe, right? And so now we have a real puzzle, because this spot here and this spot here and this spot here, all of these spots are the same temperature, 1 part in 100,000, yet there's absolutely no way for them to have communicated with each other since the moment of the Big Bang, because there hasn't been enough time for light to get from here to here. So this and this and this and this are effectively completely separate universes. They were never in causal contact with each other, yet somehow they managed to reach equilibrium in temperature to an incredible, sub-percent level. And the standard Big Bang cosmology doesn't explain this, right? You basically have to assume it is a boundary condition. You just say, well, the universe started out highly homogeneous, but there's no particular reason to expect it. I mean, it's just like kind of, well, God did it, you know? So the standard cosmology, this picture of the universe filled with matter, radiation, and vacuum that started out in an infinitely dense, infinitely hot, coming out of a singularity, the standard, what's called a lambda cold dark matter cosmology, it fails to explain a lot of the basic properties of the universe, why it's so big, why the universe is so old, right? Why is the universe, if you just plug in Einstein's theory of gravity and look at the natural sort of how old what the lifetime you would expect the universe to be, you would expect it to only live for about 10 to the minus 35 seconds, but it's lived for 10 to the 10th years, right? Why? So why is the universe so big? Why is it so old? The characteristic scales are the scales associated with gravity. You would expect the universe would just be this tiny little thing that would recollapse on itself, and that would be it. Of course, we wouldn't be here to observe it. Why the universe is so homogeneous, right? How did the cosmic microwave background get into perfect thermal equilibrium to 1 part in 100,000 when all of these spots were essentially separate universes who had never communicated with each other, right? And also, why is the universe so close to geometrically flat? You can measure the curvature of the space, right? So there are 3 possibilities depending on the density of the universe. Either you're positively curved, which means that the universe is the surface of a sphere. This is a little hard to imagine because in this picture, it's the 3-dimensional surface of a sphere in 4 dimensions. So it's without a boundary. We just live on the surface, right? But it's closed on itself. Or the universe is the opposite, which is called a negatively curved space, or it's exactly on the boundary between the two, which says that the geometry is flat. And observations, in particular observations of the cosmic microwave background, tell us that the universe is exactly geometrically flat to within we've measured it to within less than 1%, right? But in fact, the lambda CDM cosmology doesn't explain the flatness of the universe either. All of these basic properties of the cosmos that we observe it to have no essential cause in this picture of the universe. So this picture of the cosmology, as successful as it is, we can work this forward. We can understand how galaxies form. We know the initial conditions. We can see it all. We can just look at it with telescopes. Very successful. The theory matches the data beautifully. There are a couple of mismatches here and there. There are things we're still working out, but it's a very successful theory. But none of its basic properties are explained by the theory itself. So this picture we have of the universe we know it's incomplete because it doesn't explain most of these properties. And furthermore, the standard model of cosmology doesn't explain these little fluctuations either. Not only does it not explain why the cosmic microwave background is so homogeneous, it doesn't explain why these 1 part in 100,000 fluctuations have the properties that they do. And so we also want a theory that says, where did these initial perturbations come from that later collapsed to form galaxies and clusters of galaxies and so on? So these are also a mystery in this picture of the Big Bang that I've been telling you about. So we need a better theory. We need a deeper theory in order to understand these kind of existential questions about the universe. Why is it so big? Why is it so old? Why is it so homogeneous? Where did the inhomogeneities come from? And why do they have the particular form that they do? Why is the universe geometrically flat? This brings us to a more modern theory called inflation, which has its origins. It was the first paper that completely proposed an idea of inflation was by Alan Guth in the early 1980s. Earlier papers had been floating around that had gotten most of the way there, but hadn't quite put it all together. And it was Guth that really put it together finally. And the idea of inflation is that this is a period of expansion that happened before the onset of the hot Big Bang. So we now have this picture. If we go back in time and the universe would have been denser and denser and hotter going all the way back to this initial singularity. Inflationary theory takes away that initial singularity at the Big Bang and instead tacks on before that. It says what happened before the Big Bang. So instead of having a singularity, what you have is the end of this inflationary period. So this is really a theory of what happened before the Big Bang. And this theory of what happened before the Big Bang is very different. The universe was not hot. It was cold. It was almost at absolute zero. And it was completely empty, full of nothing but the energy density of empty space. So the inflationary picture, what happened before the Big Bang was and a universe that had nothing in it but vacuum. And it turns out that if you have a universe with nothing in it but the energy of vacuum, it expands exponentially quickly. And this energy of the vacuum during inflation would have been huge. It would have been an enormous energy density, which meant that the universe would have expanded enormously quickly. And so it would double and double again and double and again and double again in size, and it would double again more than 120 times at least, right? So you have this enormous, incredibly rapid expansion of the universe that happened before the onset of the hot Big Bang. And the hot Big Bang happened when this vacuum energy decayed into all the particles of the standard model. And we'll talk in a minute about the mechanism for that. And this, it turns out, sets up the initial conditions, and it sets up these boundary conditions. For example, it creates a flat, homogeneous equilibrium universe in a very natural way. And we'll talk about how that happens. But the basic idea is you're replacing that Big Bang with an earlier period of vacuum-dominated expansion. The universe was absolute zero, filled with nothing, completely empty, filled with nothing but empty space. So how can nothing be something, right? How do we do this? And in particular, this is funny because this period of vacuum-dominated expansion has to end somehow. It has to transition into this hot Big Bang. So it has to be dynamical in some way. This energy, this vacuum energy can't just be static. It has to have some kind of dynamics to it. And so in order to understand that, in order to come up with a theory of it, we're going to steal something from particle physics. And this is where people trained in particle physics like me come into this picture. And what we're going to steal from particle physics is the idea of symmetry breaking. And this is ubiquitous, for example, in the standard model of particle physics. It shows up in condensed matter physics a lot. But in order to understand symmetry breaking, I want you to imagine a pencil balanced on its tip. Okay? So now this is unstable, right? You balance a pencil on its tip, what happens? Falls over, right? You know, little air currents or even quantum mechanical fluctuations will push that thing off and it'll fall over. It's an unstable equilibrium. But it's symmetric, right? So in particular, it has a symmetry in that when the pencil is standing up on its end, if you rotate that pencil about the vertical, you get the same thing back, right? It's symmetric under these vertical rotations. But when the pencil falls over, because this is dynamically unstable, right? So that if I let the pencil drop, it can drop in any direction it wants. There's no preference, right? Because this is a symmetric state, it's equally likely to drop this way or that way or that way or whatever. There's no particular preference for how it drops, but whichever way it drops, it picks out a direction. So now the pencil lying on its side is no longer symmetric under that rotation about the vertical, or the symmetry is called broken. So this dynamically, we have an unstable state that is symmetric, and we have a stable state that breaks the symmetry, that no longer realizes this rotational symmetry about the vertical. This is a very common process in nature. You have systems that are symmetric but unstable, but the stable state actually fails to realize the symmetry in much the same way that the rotation of the pencil does. And so this pencil now also, when it's on the vertical, it has potential energy, right? And so as it drops, its potential energy into the gravitational field drops as it drops. So we can make a plot of the potential energy of the pencil as a function of its angle of tip. And so the energy is high when it's on its tip, and it's at a minimum when it's on its side. But since it doesn't depend on the direction, it makes this sort of circular thing. It looks like a sombrero, right? This is what particle physicists call this a Mexican hat potential, right? So and now the physics of this, you can think of it as like a ball rolling down a hill. This pencil tipping means that the angle of tip gets bigger and bigger, and when it's down here, you're at the stable state. So we can plot the energy of this system as like a ball rolling off the top of a hill. This is unstable up here. The ball wants to roll down and live in this trough on the bottom. Okay. When the ball's up here, it's symmetric, right? You can rotate about this and the state doesn't change. When the ball's down here, it's picked out a particular direction in this trough and the symmetry is broken. This is exactly what happens, for example, with the Higgs boson in the standard model of particle physics, where this symmetric state is a state in which all the particles in the standard model are massless. When the Higgs boson symmetry is broken, and now this symmetry is in this abstract group space, but it's pretty much the same thing as a pencil falling over. When the symmetry is broken, all the standard model particles acquire mass, and the Higgs boson itself is massive. So in order to think of this, for example, in the Higgs field now, it's not like one pencil balanced on its tip, but you have to imagine that all of space is filled with pencils balanced on their tips, one pencil at every single point in space, an infinite number of them. And then when the symmetry breaks, all those pencils fall over in the same direction and pick out a direction, a broken symmetry in that space. So the Higgs boson, for example, is an example of a field, so that when it's in its symmetric state, it has potential energy. The vacuum has energy that is the potential energy of this field that permeates the entire universe. When the symmetry breaks, when the pencil falls over on its edge, that symmetry is broken, and all of the particles acquire mass by their interaction with this field that permeates the universe. So this is how the Higgs field works in the standard model. We also borrow this for inflation. In particular, then, what we have is, in the early universe, we say that during inflation, this thing would have been sitting up on its peak. The universe would have been full of vacuum energy, but would have driven this incredibly rapid expansion. And then at some later time, this field, it's unstable, so eventually it drops off the peak. It goes down here, and this energy that it had while it was up here gets transferred into, decays into all the particles of the standard model, heats the universe up to a super high temperature, and we end up with this homogeneous hot initial state of the Big Bang that comes from the decay of this energy that was associated with this vacuum field. This is the idea of inflation. You start out with an unstable vacuum, it drives exponential expansion, and then eventually that vacuum decays, and that energy gets turned into all the particles that fill our universe today. All the hydrogen and helium and dark matter and quarks and electrons and positrons all come from the decay of this vacuum energy that filled the zero temperature universe before the Big Bang. So, and this is very directly analogous to the Higgs boson in the standard model of particle physics. We have examples of this that we know work in particle physics itself. So this expansion, this vacuum expansion, has a neat property in that the expansion of the universe, instead of slowing down, right? If it's full of dark matter or something, the self-gravitation of all the galaxies, you would expect it to gradually slow the expansion down. When the universe is full of vacuum energy, the expansion of the universe actually speeds up, it accelerates. So now, instead of seeing more and more of the universe as time goes along inside our observable universe, during inflation, your observable universe stays approximately constant, but the universe expands exponentially quickly. So somebody who starts out inside your observable universe very rapidly gets stretched outside of it. This explains the homogeneity, right? So these guys can start out, this little patch of the universe starts out being pretty much homogeneous because everything can talk to everything else. But then the expansion is so rapid that that little homogeneous patch gets stretched out way bigger than the observable universe, and stretches out and explains why the initial condition for the Big Bang is homogeneous and isotropic and flat and all of these things, right? So inflation also explains the flatness of the universe, because if I have a little patch, for example, on a sphere, and if I'm on a very small planet, I could actually see the curvature going out to my horizon. But if I blow that planet up really huge, my local area looks perfectly flat. My observable universe my horizon looks perfectly flat, just like on the Earth, right? It looks flat to us all the way out to the horizon. So the way inflation explains the flatness of the universe is if there's a little bit of curvature initially, it stretches that out so big that you can't see it within your observable universe. And in particular, you get something for free when you add quantum mechanics in here. The vacuum isn't actually empty, it's full of little virtual particles. Quantum mechanics tells us that the vacuum is really a very busy place. And these virtual particles, or these quantum fluctuations, also get stretched with the expansion. So they start out smaller than the observable universe, and they get stretched bigger than the observable universe. This is like, you maybe heard about Hawking radiation from black holes, this idea that you have a virtual particle pair that's produced near the horizon of a black hole. One of them falls in and the other one escapes. How many people have heard of that? All right, this is exactly the same process as Hawking radiation, except here you have a virtual particle pair that pops out of the vacuum, and the universe is expanding so fast that they get stretched outside each other's observable universes before they can recombine. And this is the process which creates those initial fluctuations in the universe, those fluctuations we see in the cosmic microwave background. And it's predictive. It predicts a very particular statistical form for what those perturbations in the CMB ought to look like. So you can give me a particle physics theory at very high energy. I can turn the crank and I can calculate via this process what the fluctuations in the cosmic microwave background we observe ought to look like. And it matches them exactly. So this is now, this process of these quantum fluctuations getting stretched out to these huge, long super horizon scales allows us to actually have observational access to this period because this is when the fluctuations that collapse to form galaxies were actually formed. They were formed by quantum mechanics during inflation. And it's a predictive theory that we can actually go out and check in the cosmic microwave background, and it's been successful, right? So this pattern of primordial perturbations actually is predicted by the inflationary theories. And in fact, it was predicted before they were observed. And these fluctuations actually match the predictions of inflation to extremely high precision. So this is, now we're not doing philosophy, we're doing real science. We can actually test models of inflation by using the cosmic microwave background, the distribution of galaxies, and so on, because it is quantum mechanics during inflation that set these initial conditions for all the structure in the universe to form. So quantum fluctuations, the same fluctuations that sort of structure in the current universe. Here's the thing, if we're looking at this thing rolling down this hill, this thing is going to be bouncing around a little bit because of quantum mechanics, right? Because of the Heisenberg uncertainty principle. And quantum fluctuations are as likely to push this thing up the hill as down the hill. So when these fluctuations are big enough, in fact, this thing keeps getting pushed back up to the top of the hill again. So as it falls off, sometimes it will fall off and go all the way to the bottom, but sometimes quantum fluctuations will push it back up to the top again. So in this picture, because of quantum mechanics, if those fluctuations are big enough, there will always be regions of the universe where inflation continues to go on forever. Those regions are getting bigger exponentially quickly. So you will have inflation ending locally, but in a bulk in between them, it will still be going on because the field will be quantum fluctuating back up. This is called eternal self-reproduction or eternal inflation. And so the picture of the universe that you get out of this, when you add this, when you take quantum mechanics into account self-consistently, is not that this process of vacuum decay happens once and then once and done. It happens in one region, but then there's going to be other regions outside of it that are still inflating. And then there are going to be other regions that decay into a different vacuum, and there are going to be other regions that decay and so on. And so the picture you end up with of the universe is a little bit like a glass of beer, right? So in this metaphor, right, the beer itself is the inflationary part where the field is in the symmetric state. In fact, bubble formation in beer is a phase transition of exactly this kind of type. It's a form of symmetry breaking, right? And so when the beer is the unbroken state, when the field is up here and the universe is expanding exponentially quickly, but then it decays down into the broken state only locally and forms a little bubble like that, and that bubble wall expands out faster than it expands outward at the speed of light. But these bubbles are being pulled apart from each other faster than the speed of light, so they never run into each other, they never percolate. And so you just keep producing more and more and more bubbles, an infinite number of these bubbles. And each of these bubbles contains within it an infinite universe like our own. And the way this works is if you draw a diagram of space and time, right, this bubble that is expanding outward at the speed of light, if I plot time on the vertical and space on the horizontal in the right unit, so that time is in seconds and space is in light seconds, or time is in years and space is in light years, this expanding bubble wall makes a 45-degree angle or sweeps out a cone in here, right? So I can do this again. So this bubble is expanding outward in space, but in time then the edge of that bubble actually sweeps out a cone in space-time. And in relativity, since I can borrow space and turn it into time, or borrow time and turn it into space, I can take some of that infinite future time and turn it into an infinite space, and I can nestle an infinite universe inside that finite bubble. So to someone outside the bubble, it looks like a sphere that is expanding outward at the speed of light. To someone inside the bubble, it's an infinite universe. And the bubble wall is everywhere in your past. It's not a boundary in space, it's a boundary in time. This is now what we replace the initial singularity with, is that end of inflation, when the universe goes from a symmetric state into an asymmetric state. It creates an infinite universe inside this finite bubble. It's kind of like some sort of magic thing from Harry Potter or something, right? And so then what we do is time goes this way and space goes that way, and we have a nice infinite universe that comes into being all at once as a result of this bubble nucleation in our beer glass universe. And this is happening continuously and goes forward in time infinitely. This happens an infinite number of times, and so the inflation never ends. It's just continuously producing new universes like our own. They're all causally disconnected. You can never travel from one bubble to another because you'd have to go back into the past before the Big Bang to get out of your bubble. And so in this picture, then our universe is just one of many and many, many. And this is reminiscent of the Renaissance philosopher Giordano Bruno, who wrote, God is infinite, so his universe must be too. He's glorified not in one, but in countless suns, not a single earth, a single world, but in 1,000,000. I say in an infinity of worlds. Giordano Bruno wrote in Cause, Principle, and Unity that to know the universe is to know nothing of the being or the substance of the first principle, because it is like knowing the accident of accidents. He was grappling with the same problem as modern cosmologists with a remarkably prescient sensibility. Bruno's resolution of the paradox of Aristotle's paradox of the first mover was to adopt a radical expansion of the Copernican principle that the Earth was but one of an infinity of worlds. So he was more Copernican than even Copernicus was. And this Copernican idea provided Bruno with an organizing principle through which to comprehend an unbounded and ultimately unknowable cosmos. And in inflation, we see Bruno's infinity of worlds extended to an infinity of universes, of which ours is but one. And of course, this is the source of the title of my book, which you can pick up outside if you like. And I thank you very much for your patience and listening, and I'd be happy to take questions.